Okay, so thanks for that introduction. So let's get started. So I wanted to talk about and introduce to the world what's we're calling Spark Cyclone. The title of the talk is Accelerating Spark with the Hidden Supercomputer Device Plugin in Hadoop. And I'll get to why it's hidden in a second. So first, let's go over the agenda of the things I want to talk about today. So first I'll go about myself, a little bit about myself, not too much. Then I'll go do introduction of the project, explain what the SX-Aurora TSUBASA vector engine is. Then I'll go into details about what's inside the vector engine, what makes it special or unique, and how it fits into the Spark accelerator landscape. There are many different tools available these days for accelerating Spark workloads. And then I'm going to go into the implementation details of Spark Cyclone, and then finally compare how it runs versus a V100 using Rapids from NVIDIA. And then finally, I'm going to go into some future directions. Okay, so about myself, I've been mainly working in Japan most of my life. I went to Japan in 2006 to work, and then I've kind of been here since then. In 2015, I worked with the SSDC, which was a research organization, and that's kind of where I got really into machine learning and deep learning and doing that at the enterprise level. And that's when I kind of joined SkyMind. In 2020, I started Express AI, which is a new company, and I recently released a book, as we mentioned before. So let's get into the project. So the project is called Spark Cyclone, and its main job is to bridge Apache Spark and put it to the vector engine. Now, there is a project available from NEC that does this. It's called Frovetis, but Frovetis works in a way where it's a compatible API that you need to change your code to use. But Spark Cyclone's goal is to make it so that it's just a plugin, so you don't need to recompile your Scala code or change your code in any way to take advantage of the vector engine. And this is going to be open sourced on November 1st, and it's super easy to set up. So I mentioned earlier that it's the hidden supercomputer architecture in Hadoop. And the interesting thing about this is that it's already built in. So if you're using Hadoop 3.3.0 or later, it already has the plugin, the Yarn device plugin for the NEC vector engine. And it kind of works alongside GPUs and FPGAs. So you just set it up the same way you would set up those different devices, and it works. And it kind of integrates with the Yarn, and and then it'll schedule the resources appropriately. So what is the SX-Aurora TSUBASA vector engine, and what are all these names and numbers or names and letters mean? Very quickly about like where this came from. So the most famous, I think, iteration of the SX series of computers, like computer architectures from NEC, is the Earth simulator. And that was a supercomputer made 20 years ago in 2001, 2002. And it was the fastest supercomputer in the world at the time for quite some time. And it was used to do climate change modeling and simulation, and also weather prediction, tsunamis, and things of that nature. Hence why we think the name Spark Cyclone really kind of fits with this project. And so that one, I think, was like the SX4, and then went with XX9, and then there's the ACE, and the newest one is called the SX-Aurora TSUBASA. Tsubasa means wing in Japanese, so that's what the cards kind of look like wings coming out of the motherboard, I guess. And so that's the new architecture. Now, the interesting thing about this is before the Tsubasa iteration, the latest one, the vector engine was the CPU, right? So it was the thing that was running the OS. So it's quite a capable CPU. It's not a special DSP-like thing. It's, a very capable superscalar type of processor. And it's being used in the latest Earth Simulator 4. You can look at this article here if you want to go into the details. It is very, very big. maybe not the biggest supercomputer in the world these days, but with 19 petaflops and 5,000 vector engines, it's plenty fast. So yeah. So let's go into the vector engine and see what it's made of. So the interesting thing about the vector engine is that it has the really high bandwidth, essentially, right? It has this, it doesn't skip leg day. It has a very powerful CPU and a lot of bandwidth to memory, and it has a lot of memory too. So it's a very balanced CPU in that sense. And so the interesting thing about the CPU is that it has the SPU, which is the part of the CPU that works with regular instructions, the same kind of instructions you'd have on an Intel machine and so on and so forth. And then it has the VPU, which is the place that does the vector processing. And it is capable of doing, the single core is capable of doing 614 gigaflops per core, which is interesting when you think about it in other things. I'll get into that in a bit. And it has 3 terabytes per second across all the cores, right? The aggregate bandwidth between the cores is that high, and the aggregate bandwidth to the HBM2 modules is 1.5 terabytes per second. And that's pretty good. The vector engine came out a couple of years ago, and it's only recently that NVIDIA has came up with a card that is capable of doing that kind of bandwidth, which would be the A100. And yeah, and so if you put all the cores together, there are 10 cores in the maximum configuration, you can get 6 teraflops per card and 48 gigabytes of RAM. And if you put 8 of these into a system, you can get up to 49 teraflops. So it's pretty powerful and very significant. Now, one thing to kind of put this into perspective is Tesla recently announced their Dojo computer architecture for deep learning. And I want to highlight it and compare and contrast it to the vector engine because there are some similarities, but some very important differences. So for example, this is what the Dojo supercomputer core looks like, yanked straight from Tesla's presentation about it. And you can see it has these 512 gigabyte links between the cores. It has an in-order CPU, so it's more DSP-like. And it has these matrix multiply systems and 1.25 megabytes of SRAM. So one of these cores, when working in 32-bit floats, I'm not sure if it does 64-bit floats at all, but at least in 32-bit floats, you can get 64 gigaflops for this single core. So it's definitely less capable, but it's also, it's made to be scaled out. So it will reach up to the same kind of performance if you scale it up enough. So while the vector engine has 10 cores in a single card, the chip in the Dojo has 350 cores, right? So it's kind of that classic argument of, do you want a lot of less powerful cores or a smaller number of more powerful cores? And I think in general, when doing analytics, the smaller number of more powerful cores is going to be probably the way to go. Another thing about this, Dojo core and also many GPUs as well, is that they're not made for doing 64-bit, right? They're actually very, very fast if you go down to 16-bit or 8-bit calculations. And another thing you'll notice about this is there's no DRAM, right? Like every core has 1.25 megabytes of RAM. And yeah, you're going to have to really work out how to schedule things on this. So these chips are very powerful for doing deep learning, and I think they'll be absolutely excellent at doing it. But when it comes to doing analytics, I don't think that these chips or any of the other deep learning focused chips are going to cut it. But the vector engine does. And of course, I would say the main kind of competitor in this space would be the GPUs in Spark, right? And so up until the A100, all your GPUs that you're going to get are going to have less memory bandwidth. So that's one difference. And they have, their performance, the performance numbers that they have, which are, like kind of cheating because they only apply to, matrix multiplying when doing low precision. The real kind of performance in teraflops that they have is sometimes significantly less and hasn't really risen that much compared to previously. So only the top of the line GPUs from NVIDIA, I believe there's many different configurations, but like the P100 and the B100 and the A100 are the only ones that really support 64-bit. But I think more importantly about this is how fundamentally different they are to code, right? As they have hundreds of threads and the way they work, you kind of have to have a different programming model. It's very difficult to take code that runs on a CPU like an Intel CPU and run it on these GPUs with any sort of efficiency. And that's actually incredibly important for us, in which I'll go into in a second about how we implement things. So if we were to put the vector engine in the whole landscape, I say that there's different options now. You have CPUs, you have FPGAs, you have GPUs, and the vector engine. And FPGAs, they're not my specialty, so I can't really comment too much on them. But they're mainly made for doing a lot of kind of bit calculations, kind of DSP-like things, very, very parallelized. So when dealing with things like 64-bit numbers and these kind of large data sets, I'm not sure if they're going to be very cost effective. I'm sure they're going to be quite performant if you're able to program them, but they're also very different in how you program them. So there might be a limited compatibility with Spark things. And GPUs are kind of, you sometimes, to get really good performance, you have to sacrifice accuracy. And sometimes in big data, that's not something you want to do. So the VE is really, I find it as a really good alternative to the CPU, right? The CPU is definitely very good, in general. But the VE, you don't have to sacrifice a lot of things to get good performance. And later on, I'll show you exactly what that means. So now let's go into Spark Cyclone and how it works. So enabling the plugin is very simple. So once you have the plugin, old name is Aurora for Spark, but we've changed it to Spark Cyclone. You just set it in the class path of the executors, because we do need it on the executors. You add it into the jar files of the driver, and then you enable the plugin. And then finally, what you do is you can tell Spark or Yarn, depending on how you're doing things, how many vector engines you want to use, right? So you can say 1 or 8 or 64, however many you have. And then finally, you can specify a cache directory for kernels. So one of the ways that we work in this plugin is that we generate C++ code and we compile it. And the first time you do that will take a little bit of time. But as long as you're kind of executing the same kind of queries over and over, we can leverage that cache instead of compiling everything from scratch. And that really raises the performance quite a lot. So one of the benefits of the Spark Cyclone plugin compared to others, the alternative, which is Frovetis, even though we build on top of Frovetis, what we do aim to do is make the plugin fit directly into the ecosystem of Spark, right? So you can still, in the Spark UI, see your plan, this native aggregation evaluation plan. This is from us, right? So we fit right into the same framework. You can debug the executors. You can see all the same metrics and everything. It works well. So it's great for doing things, and you don't have to change any of your code. Again, you just integrate the plugin and you're good to go. So how we do this, compilation, for those who aren't really familiar with the how Spark does plugins, you can kind of simplify it to this. This is like the main flow. But essentially, the plugins, the Catalyst plugins in Spark can fit right in between that logical plan and the optimized logical plan in this workflow that everybody uses. And what we can do is we can look at the logical plan, analyze it, match it against things that we support currently, and then change that plan with our own physical plan, like physical evaluation nodes, right? One of them that we have is the native aggregation evaluation plan that I was talking to before. And then once we pass that back to Spark, Spark will eventually get to the execution part of that plan. And when we execute that plan, we then evaluate, the table. We know if we can use the hints of whether the columns are known to be null or not null. And then we can generate some C code that specifically targets, that type of data. And then we compile that into an SO file using the NEC compiler. And then once we have that, the executors, get to work, and the first thing they do is they fetch that SO file from the driver, and then they load it into the vector engine using something called VEO, which is vector engine offloading, and that's how they execute the code. We copy the data into the vector engine, execute it, and read it back. So I can go one more level deeper with the aggregations here. So this is an example of some of the code that we have. And this is the declarative aggregation converter. And I think it's very interesting. So in general, the way that it works is we take the declarative aggregate that Spark has, right? So you can specify, for example, correlation or sum or these kind of things, which are all kind of defined in Catalyst. And what we do is we convert that to code by specifying the different phases that we have in the C++, right? So one of the things that we need to do in the C++ is allocate the memory for the partial results and the final results, right? And then we transform that. We do the iteration, so that's when we're doing the main loops of the thing. And inside of those loops, we'll have our compute section. And then finally, we need to take the partial results and copy them into the outputs. That's the fetch things. And then finally, we have free, right? Because this is C++ we're talking about. And since we're generating C++ code, we need to make sure that it also frees all the memory that it uses. And then finally, there's that last part, which merges two different things. And these prefix strings that you see are just our way of having everything share the same scope, but have different prefixes for variable names and things like that, which is kind of important for the vector engine, because as a vector computer, it takes for loops and essentially turns it into a single instruction. So you kind of want to avoid like function calls and those kind of things. So what's I think is really crazy about this, which makes it really interesting from my own perspective as a project, is that if you look into the source code of Spark Cyclone, you will not find, for example, an implementation for the correlation function. And that's because we compile the expressions from Scala directly into C++. And I can even show some of that very quickly. Let me see if I can bring up the IDE real quick. So for example, this code that you see here on the left eventually becomes this kind of code here. So this is so you can see there's this X average and these things. So we kind of take these expressions here and then we generate the C++ code from that expression and continue on. So it allows us to implement a lot of functions without having to kind of go through the slog of re-implementing every single type of method that Scala implements. Now, it does mean that sometimes this code might not be ideal for the vector engine, but since the vector engine is quite CPU-like, it turns out that this isn't so bad. Now, there's still room for improvement, and specifically in a certain number of queries that we're looking at. So one of our challenges in this project is how do we take these Scala expressions and kind of make it into a compiler so that we're generating efficient code for the target, whether it be the vector engine or possibly others. The other thing that we're doing that I think is actually incredibly interesting is that we're using Lee Howey's source code module, which is actually really great. So some of these features are actually available in C#, where you can say, like, what is the name of this parameter, and then use that in debugging strings. But we're also able to use this in here. And one of the things that we do is we have this kind of code lines debug here. And what that does, if I bring back the source code that we generate, is you can see it knows which method it is coming from and what line it's at, right? So this is the line in the Scala code, and then this would be the line in the C code. And we can use that to do some print line debugging, so we can see how long each one of these phases is taking when it's executing on the vector engine. So that's very cool stuff. And yeah, we also implemented things like tracing and things like that, just so that we can be very thorough in measuring the performance. So speaking of the performance, I think many of you are wondering, how does it compare to a GPU? So I would like to compare it to the A100, but they are very, very difficult to come by right now. We do have some V100 machines, and so I can show you the performance of the vector engine versus the V100 when using our plugin. So before I go into the details, just a quick note about the methodology that we're doing here. So what I chose to measure here is the TPCH queries. And the way they're implemented is we downloaded the PDF from the TPCH website. I took those SQL queries, I copied and pasted them into Spark SQL blocks, and that is what we are running. Now, all tables were cached before the querying, so we called cache table whatever for all for all the tables that are available. And then we execute the query and collect all of the rows, and we print the rows for verification, but the printing part is not measured, right? So for us, it's, we measure the time it takes to execute the SQL and collect all of the results, but not print the results. So it's very realistic in terms of what you would expect from your own, from actually using it. And we used the vector engine type 20B, which is not the fastest, but it is one of, it's almost there. And then the NVIDIA V100 16 gigabyte. And we ran these at 3 different scales. So TPCH has different scales. 1 is a 1 gigabyte data set in total. 10 is a 10 gigabyte version, and 20 is a 20 gigabyte version. All the outputs are exactly the same between CPU and GPU and the vector engine. So there's no cheating, yeah, so it's pretty thorough. With a little bit more work, this could possibly be a proper TPCH benchmark. So at 1, which is the 1 gigabyte benchmark, you can see this is kind of like the raw data. It's the ratio of the performance, right? So at 1, that means that the vector engine and the GPUs take the same amount of time. And as you can see, in general, we are winning out. There are some queries that we're looking into, like 10 and 14, those are going to actually be an issue throughout the other ones. And 16 through 19, in general, like they seem to be very difficult, right? So difficult for the GPU, difficult for us. But like for example, query 9, that's a humongous boost. Like it's like 1 second versus 20 something seconds. It's a very big difference for that query. So this is kind of what I was mentioning about how the vector engine has a lot more balance when it comes to the performance to the bandwidth. And the bandwidth difference, as the V100 has 900 gigabytes per second of bandwidth, should be about like 1.6, right? So seeing the number 2 kind of come up a lot is important. And the more complex the query, the more the bandwidth kind of comes into effect and comes into play at this. So 1 is very small, so let's skip this. Let's take it up a notch to 10. So when we go to 10, we can see that there are definitely some problems in our plugin. It's still very early days, and we kind of know where the problems are, particularly in query 10. These are all string-based ones, and we're kind of using an inefficient string representation at the moment. But you can see it's a very similar thing, right? 16, 17, 18 are very similar, but a lot of these queries have significant performance advantages on the vector engine versus the GPU. And then finally 20, and 20 is interesting because 20 is now bigger. The data set is bigger than the GPU memory, because the GPU has 16 gigabytes of memory and the vector engine has 48. So now you can see, even though in 10 it was not so great, in 20 now everything is just a little bit bigger in terms of the query performance. So yeah, so I think we're really on to something here, and we've just barely started, right? Rapids has a humongous team working on it, and I'm sure maybe there's some tuning magic that they've done. I did spend quite a lot of time trying to tune the GPU to work correctly. Maybe I'm doing something wrong. There's a ton of parameters, but like the out-of-box experience with the vector engine is showing really good results. And when you take it down a notch and use Frovetis, the results are even better, because just the way Frovetis is kind of mostly C++. So yeah, so that is the performance. Now let's talk a little bit about the future directions before I wrap up here. So like I mentioned, there's so many low-hanging fruit available to us right now that we're not even close to the limitations of how much performance we're going to get. I still think there's still room for improvement. So one of the things that we don't do is good column caching. And I think that caching is something that we could do to really accelerate some of these queries if we can limit the amount of copying that goes over the PCI Express bus, because that doesn't have high bandwidth, but the main memory of the vector engine does. And the other one, which I think is super exciting, is x86 mode. So Frovetis doesn't only support the vector engine, it also supports CPUs. And so I'm very interested to see, for example, how Spark Cyclone compares in terms of performance versus the things that Intel is doing with their Oak toolkit, right? So this is something that we're going to try to look into sooner rather than later, but it could be very, very interesting. The other thing, which is part of how the GPUs kind of get their performance, is doing things like shuffling over RDMA and things like that. And we can do the same thing in the vector engine. If we can shuffle over InfiniBand using RDMA, I think that, and do it vector engine only, we could have significant improvements in performance, even more than what we have right now. Utilizing Scala native is an interesting one. So I do actually have Scala native compiling binaries for the vector engine. So NEC has created a fork of LLVM that does create binaries for the vector engine. And I have done hello world things on Scala native on here. And I'm very interested to see where we can take this, like how far can this go? The other kind of major challenge that we have is optimizing the C++ code from the Scala code. So we kind of need to make our own compiler, an optimizing compiler, to optimize that C++. And of course, I think one thing that can always be better is to kind of raise our abstractions a little bit. We are still kind of dealing with strings more than I would like. I would really like to have, things like a C expression. Well, we do have a C expression class, but like a C variable, those kind of higher level abstractions from Scala, and then kind of use that in a monadic way, or like a free monad way to generate code, and then also pass those through an optimizer to do the one before. So these are all our challenges. If those things look interesting to you, please visit our jobs website and sign up, or visit our booth. We're just going to be there. You can talk to us. You can geek out. We don't really care. If you are looking for a job, or if you're thinking about remote, we are a completely remote company. This is, we do our work on GatherTown. We're doing a lot of stuff in the AI side of things, not just in the analytics side of things. So I think we have something for everyone. So yeah, if you saw something interesting here, feel free to visit the booth or visit the website and send us your resume, and we're happy to talk to you. Okay, so that is everything I wanted to talk about.